Homework 2, I finally got that graded, what was that, Saturday night, and then I came in here and photocopied them all Sunday. So those are submitted. Homework 3, I'd like to sort of not put it off as long as time, so I'll start grading those tonight and it should be back by Wednesday. I'll post up solutions to that as well, and I guess as soon as you turn in homework 4 on Wednesday, I'll post up solutions as well, so then we'll be back on track. As for today, again, none of this stuff is on the exam, but we have to keep going. And we were doing congruence conditions for triangles. We did, what do we do? SAS is a postulate. SAS is a postulate. What did we do last time? We did ASA last time, and you'll recall AAS is also a congruence condition for triangles. So we'll state it formally, but I'm sure you already know what AAS means, but if the vertices of two triangles are in one-to-one correspondence, such that two angles and the side opposite one of them in one triangle are congruent to the corresponding parts of the second triangle. Then the triangles are congruent. Right, so two angles, and I always think of these sequentially. I think of sort of going around the triangle, and you've got angle, angle, and then a side. But I really like the way this is phrased, because angle, angle, side doesn't really write that well. The way this is phrased is saying two angles and then the side opposite one of them, which is more precise, I think. So this is nice. This will be true in neutral geometry as well. It's not just a Euclidean result. The proof starts, and we get almost to the end, basically doing exactly the same as we did for ASA. So I'll just start writing some stuff down, but it'll start basically exactly the same. So let triangle ABC and triangle DEF be two triangles such that our hypotheses hold. So they match up in an AAS sense, such that angle ABC is congruent to angle DEF. I think I'll draw them over here, so we'll go to the second line. Angle BAC is congruent to angle DEF. EDF. And side AC is congruent to side DF. So let's see, let's draw two triangles. ABC, DEF. And we'll fill these in. We'll make sure we actually have AAS here. ABC is congruent to DEF, so ABC DEF, good. BAC, angle BAC is congruent to EDF. BAC congruent to what? EDF, this one right here. That's good. And one of the opposite sides should be congruent, one of the pairs of opposite sides. So we're going with the angle opposite. Angle A, it's side, oh sorry, actually opposite B. Side AC is congruent to side DF. Okay. So there's AAS, right? Two angles and one of the sides opposite one of the angles. And we want to show that therefore they're congruent. So once again, let's say we can show that either one of these sides, suppose I can show that AB is congruent to DE. Then we're done, right? We're done two different ways. If these are congruent, then I'm done through SAS, or I could be congruent through ASA, which we've already proven, right? So that's our goal. Show that one of these pairs of sides must be congruent. If either AB is congruent to DE, or BC is congruent to EF, then the triangles are congruent. Triangle ABC is congruent to triangle DEF, and we're done. And this follows by SAS or even ASA. Since we've proven ASA, you can use it now. So we'll do exactly what we did last time. We'll say, well, okay, suppose they're not congruent. Suppose AB and DE are not congruent. Then one of them must be longer. So we'll choose a point on the interior of AB so that the A to that point is the same length as DE. This is exactly the same as the proof we did at the end of last class. So let's start a new paragraph. Suppose, for sake of contradiction, that they're not congruent. AB is not congruent to DE. One of them must be longer, so without loss of generality, we'll say that AB is the longer side. So the length of AB is bigger than the length of DE. Then there is a point that I'll call B prime. Call it B prime. On side AB, we'll choose a point B prime on here, such that A, then B prime, then B. And such that the length of AB prime is the same as the length of DE. And again, just notationally, I'm saying that the measures of these sides are the same length, or the sides are the same length. If I were to talk about the actual sides, it doesn't make sense to say they're equal, say they're congruent. I'm just using this slightly stricter notation than we use in Geometry 1. Either notation is fine though. So what do we have? So now we're in the same situation as we had in the proof of at the end of last class. I've got a smaller triangle built inside of this one. AB prime is the same length as DE. So now I can invoke SAS to conclude that this triangle AB prime C is congruent to DEF. right, just by construction. So I'm going to erase most of this. Okay, so hence, should I say hence, maybe therefore, I don't know. Hence, triangle ABC is congruent to, AB prime C is congruent to triangle DEF. Once again, by SAS. And therefore, well, first thing I can say is that the measure of this angle, measure of angle AB prime C, must be the same as the measure of angle DEF. All right, that's why the congruence we just established. If this triangle is congruent to this one, then these angles must be the same. But by our original hypothesis, these two angles are the same. ABC and DEF are the same angle. So all of these must be equal. This must be equal to the measure of angle ABC. So these two angles, we've concluded, have the same measure. By the picture, that's clearly not possible. But we're not doing proofs by diagram here. Last time we had this situation, we chose a point in here, and we claimed that this angle and this angle were the same. And the way we concluded there was a contradiction was by saying, well, this point is interior to this bigger angle, so this angle must be smaller. Try to come up with an argument for me. Try to argue why these two can't be the same. So take a minute, because this is where the proof diverges from last time. Take a minute to try and come up with a formal argument for why these two angles can't possibly be the same. Think about that for a second. I'll give you a big hint. Use the exterior angle theorem. There's another way you can do it. So yeah, what I have here, look at this triangle. Look at this triangle in orange. This is an exterior angle, right? What does the exterior angle theorem say? It says exterior angles are bigger than the other two angles. Right? So this angle by the exterior angle theorem must be bigger than this one. That's a contradiction because we've already concluded that those two angles must be the same. So now angle AB prime C is let's say exterior to angle CB prime B. Actually, let's go the other way. Let's call it B. B prime C. So angle ABC, the measure of the angle, AB prime C must be bigger than the measure of angle ABC. Now let's call it B prime. No. Sorry, there's too many letters here. What angle am I looking at? I'm looking at this angle. B prime BC, which is of course obviously the same angle as ABC. All right, once again, I think we have all the notation correct. I believe that's right. This angle is exterior to this one, so this angle must be bigger than the other two, so this angle is bigger than this guy. But we've already concluded that if side AB is not congruent to DE, then those angles must in fact be the same length. So there's our contradiction. All right, and therefore, the measure of angle AB prime C being equal to the measure of angle ABC is a contradiction. So we must have, I'm running out of words to use here. Therefore, hence, I guess we'll just go hence again. Let's just say so. So we must have that AB is congruent to DE, and hence the two triangles are congruent as we wanted. By SAS, as we established, would be true earlier. Any questions? Yes?
I don't think we can use BC and EF.
You don't think we can use what?
BC congruent to EF.
B.
I don't know
I don't need it. I haven't assumed anything about BC and EF,
why.
right?
You said if AB congruent to DE
Then-
or BC congruent.
Or yeah, so either one has to be true, and we showed that this one is
I don't
true.
think BC is work.
Coming in?
I don't think another one is work.
The same argument will work, right? It's completely symmetric. You just have to do the same argument over here. So you assume BC is longer than EF, take a point, build the same picture.
Yeah, but no SAS or ASA.
No what?
SAS or ASA.
Yeah, you'd still have SAS because we'd have right by our assumption this. Hold on. Why did I? We have this. So I don't even need this. Oh wait. If I have that. Yeah, you're right, maybe it's not or. Maybe I had to do side AB and DE. I'd have to think about it. But the point is, we're done, right? I don't have to care about the side at all. Once I've established that these are congruent, we are indeed done, okay? So, yeah, maybe or. Or no, it's still or. If we could have shown it, if we could have shown it, we would have been done by SAS, but I'd have to think about the argument. I'd have to. Right. In any case, what's our last one? We have SSS, right? We're not doing that right now. We're gonna do something else, which is we have the isosceles triangle theorem. It says if two triangles are isosceles, then their base angles are congruent. The converse is also true. We know the converse is true in Euclidean geometry. It's true in neutral geometry. It doesn't rely on any sort of parallel postulate. So the converse of the isosceles triangle theorem so if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So again, this is a nice result to have. It says sort of that at least some of the basic things you'd want to be true that you're used to working with in Euclidean geometry are still true. And to prove this, it's actually nicer to prove the contrapositive. So we're going to prove the contrapositive. What does that mean? So we're going to assume that two sides of a triangle are not congruent and show that the angles opposite them can't be congruent, right? So suppose triangle ABC is such that side AB is not congruent to side AC. One of them must be longer if they're not congruent. So we'll suppose, without loss of generality, that AB is the longer side. Let me draw this so that this is clearly longer. Okay. So here's A, B, C. Not a whole lot longer, but I've drawn this so that AB looks a little bit longer than AC. And what are we going to do? So once again, because it's longer, we can find a point that gives us the same length and so on. So there exists, let's just say find or choose. It's a unique point. Find the point. Find the point D on side AC, extended ray AC, such that A, then C, then D, and so that AD is congruent to AB. Okay, so AB was the longer side, AC is the shorter side. What I'm saying to do here is,
Are we assuming that they're not congruent?
yes,
You just need a little stick.
suppose, not congruent, thank you. So this is slightly different than what we've done before, and I've actually, I think the first time I tried to prove this, I tried to say, well, AB is longer, so let's put a point inside. So what we're gonna do here is the opposite, we're gonna say AC is shorter, so we're gonna extend this. We're gonna extend this ray to a point D and build a bigger triangle. Alright, so AD is now the same length as AB. Why did I do that? Well, now I have an isosceles triangle, right? AB and AD are the same lengths, so these two angles must be the same. And we have a lot to work with here. So, let's see. By the isosceles triangle theorem, which we're allowed to use, right? We can invoke this. We're proving the converse. We've already proved the isosceles triangle theorem. By the isosceles triangle theorem, we have that angle ABD is congruent to angle ADB. And moreover, angle ACB is an exterior angle of triangle BCD. Hence, here's the conclusion we're going to make. The measure of angle ACB is bigger than the measure of angle ADB. See if we believe this. Do you believe this? So what am I claiming? I'm claiming angle ACB, so let's find this angle right here. I'm claiming that this angle is exterior to this triangle, BCD. It's an exterior angle. So this angle ACB being exterior must be bigger than either of these two opposite angles. So I'm claiming by the exterior angle theorem, this angle is bigger than this one. Okay? So finally, since point C is interior to this angle ABD, point C is interior to angle ABD, it follows that the measure of angle ABC is less than the measure of angle ABD. I hate using inequalities with this angle sign because my less than look exactly like my angles, but try to read this. I'll try to be good with my handwriting. Okay, so all I'm saying here is that this angle C, or this point C, is interior to this big angle, so this one has got to be smaller than this big guy. And I think we're done. We just have to string a whole bunch of stuff together. So, do you believe this inequality so far? C is inside A and D, so this angle here is smaller than this bigger angle. But what's this bigger angle equal to? Well, that bigger angle is equal to this angle, because this is an isosceles triangle. All right, so ABD is the same measure as ADB. right? So this is because it's isosceles. And all that work earlier told us something about the measure of angle ADB. That it's strictly less than the measure of angle ACB. All right, by this work done up here. So what do we have? We have that angle ABC, this angle, is less than this angle. Meaning they're not congruent, which is what we wanted to show, right? If these two sides were not congruent, then the opposite angles are not congruent, which is the converse of this statement. So I'm out of space, but therefore angle ABC is not congruent to angle ACB, and we're done. We've actually done a little bit more here. We've done a little bit more, and I want to state this precisely. Right, in our proof, we've actually proven more than the converse of the isosceles triangle theorem. We didn't show only that if two angles aren't congruent, then their opposite sides aren't congruent. We have an inequality here which tells us which angle is bigger, right? We assumed that AB was the longer side, and we showed that the angle opposite the longer side is the bigger angle. Again, an obvious statement in the Euclidean sense, but it's true in neutral geometry as well. So we'll state that as a theorem. Actually, I mean it's proven right here in this proof. So we'll state it as a theorem. So note that the proof shows more. Right? It shows the following. And we'll state this theorem. It's if two angles of a triangle are not congruent, then the sides opposite them are not congruent. This is the contrapositive of the converse of the isosceles triangle theorem. So then the sides opposite them are not congruent. But moreover, the larger side is opposite the larger angle. So worth keeping in mind. And I think we have just enough time to do one more proof. So lots of proofs today, but we need to prove one more thing. Still, we're not getting back to SSS. Even before we do SSS, we need something called the hinge theorem or the hinge lemma. But this is the triangle inequality. You guys know what the triangle inequality says, right? Basically, the shortest path between 2 points, is a straight line. So If I walk along any other two lines, then I've gone a further distance. So in other words, the sum of two sides of a triangle is larger than the third side, always. This is the famous triangle inequality. The sum of the measures of any two sides of a triangle is greater than the measure of the third side. This is in fact, this is true in any setting where you can measure, have a reasonable notion of measuring distances, right? It's a property of being what's called a metric space, which neutral geometry, all geometries would be, as long as you can measure a distance. And we've only got 10 minutes, so we'll go quickly through the proof. And admittedly, if I recall, my proof is all jumbled and out of order, so we'll try and fix this on the fly, or make it read a little bit better than what I've written down. But here's what we want to do. We want to show let's draw a triangle. A, B, C. And I want to show that AB plus BC is bigger than AC. Okay, so I'm just going to take two arbitrary sides of a triangle, add them together, and show that it must be larger than AC. There's of course many different combinations here. We'll just prove this one, but they're all sort of the same proof. So this is one of many. And here's how we're going to proceed. Let P be a point on the extended ray AB such that A, then B, then P. So we're going to extend this out to a point P. And such that BP is the same length as BC. Okay, so how far did I extend this? How far did I extend this ray? Well, I extended it in such a way so that BP and BC are now congruent. So I just measured the side length BC and I extended that far. Okay. All right, we'll see if we can order this nicely. I don't think we need this just yet, but first, note that this triangle we built, BPC, is isosceles. So first note that triangle BCP is isosceles. So by isosceles triangle theorem, these base angles are congruent. So angle BCP is congruent to angle BPC. Okay, so we don't need that right now, I'm just gonna put that out there. Now, let's get back to the lengths of these line segments. In this setting, we have what? We have AB plus BP is equal to AP. So that's an obvious observation. If I take AB plus BP, that's the same length as AP. And also, B is interior to angle ACP. So I'll try to fit it all on this line because it'll look better. Then the measure of angle ACP is bigger than the measure of angle BCP. Right, so B is interior to this bigger angle, right? So because it's interior, this angle here is smaller than that bigger angle. And we already claimed that that's equal to the measure of angle BPC. That's this guy, because it's isosceles. BPC. I think we're there. We have to piece a few things together. This angle is bigger than this angle. What does that mean? By our previous theorem, that means that this side is shorter than this side, right? Longer sides always opposite longer angles, so by the previous theorem, this means that AP is longer than AC. Well, what do we want to do? We want to prove this. We have this. We have AB plus BP is equal to AP. So combining all these results, we have AB plus BC AB plus BC. Well, BC was chosen to be the same length as BP. So AB plus BC is AB plus BP. We already have that AB plus BP is equal to AP. And AP, by doing all this angle stuff and invoking the previous theorem, we've shown that AP is longer than AC. So like I said, I felt like this proof was a little bit out of order. Now that we've written it down, I think if I was going to rewrite this, and this is something that often happens when you're writing proofs, you know, this is why I like latexing, is because you can rearrange things after the fact. I think I would have started off by saying we want to establish this chain of equalities or inequalities, right? And then just go through them one by one, right? Say equality 1 follows because of this, well, because of construction. Equality 2 follows just by obviously looking at the picture, this is a straight line and this is sort of how distances work. So then all we really had to do was establish inequality 3, which followed from a bunch of isosceles triangle stuff. That would be a nice way to write this proof, I think. So anyway, we've done this one case. There's obviously other cases. You have to think about adding two sides together and being longer than the third side, but the other cases follow similarly. The other cases are similar. Any questions? Any thoughts about the exam, homework? Any questions about that stuff? Yes.
What's the exam gonna be like?
Pretty much what I said in the announcement. You can expect to, I'll give you an axiomatic system and I'll say, build a model for the system, prove it's consistent, show that some axioms are independent, maybe prove some simple results about the system. Everything you've been doing for homework this whole semester. And then probably from 3.2, maybe I'll find a simple proof or something like that. Yes?
So we don't need to have like the axioms from the different geometries that we've learned memorized?
So you don't have to memorize like Fano's axioms or Young's theorem or anything, or Young's axioms, but you should know sort of the definitions for what is an incidence geometry. So you should know the axioms of incidence geometries. SMSG, I'm not asking you to memorize all 15 of them or whatever. In fact, if you want, I can print out the axioms and give you the SMSG axioms. I don't think you'll need them for anything, but yeah. So you won't have to sort of memorize all 15 of those, but the other definitions and stuff we've talked about. Again, definition of an incidence, axis or incidence geometry. You should know this. Okay. Awesome. I'll see you guys Wednesday.